All right, so starting with number 10 here, we've got the two curling stones hitting each other, and so I'm going to go with the idea that the stones have an elastic collision. Thus, both momentum and kinetic energy are conserved. That's spelled wrong. Conserved. And let's see. Heavier one hits a lighter one. Since the moving stone is heavier than the resting stone, I think it will continue forward after the collision. All right, so that's the written part of my why. Yeah. Well, nope, you have your own copy of it, so you can use yours. All right, this is mine. All right. So, diagram-wise, do they call them 1 and 2, or what do they call them? Yes, 1 and 2, okay. So this is going to have some momentum afterwards. Momentum of 2 before is 0 because it's not moving. This will have some new momentum, so I'm going to call that momentum prime, just to use that notation. This will start off with some momentum here, and then I think it's going to continue in this direction, but be less. And if I was really being good with scale-wise, the one arrow before should be the same length as if I add the 2 arrows together afterwards. But I think my scale's off a little bit. So that would be my diagram on my Y. So let me put that in place. So this is my before diagram. All right, so I'm showing I'm understanding that it's an elastic collision. What's true of an elastic collision is the momentum and kinetic energy are conserved. And then I think because that first one's heavier, it's going to continue moving forward. That's what I saw earlier in some of our experimentation. If a lighter one, if the first one was lighter, I'd probably expect it to like bounce off and move backwards. If they're exact same, I'd probably expect the first one to stop and the second one to move. You know, but questions on the why? All right, let's go on to the how then. So, from my equation sheet, I'm going to grab that I know that momentum of the system before equals momentum of the system afterwards. And because it's elastic kinetic energy of the system before equals kinetic energy of the system afterwards, I should remember that momentum is mv, and it's a vector. Whoops. So this should be vectors. And the kinetic energy is 1/2 at the speed squared, and it is not a vector. That's all for my equation, right? So, I think we should start with momentum or kinetic energy? Momentum? Okay, let's start with momentum. So, I'm going to write, let's see how we'll go in red. Momentum of 1 plus momentum of 2 before equals momentum of 1 afterwards plus the momentum of 2 after. Now, if this had been like an inelastic collision, or perfectly inelastic collision, I'd only have one term after. But since they stay separate, I'm going to have 2 terms, because 2 bodies, 2 bodies. All right, so let's substitute in. Let's see what I know. So this would be M1, V1, and I'm slacking. I should have vector symbols on that. Plus 0 equals M1, V1 prime, plus M2, V2 prime. Just applying my definition of momentum. Stop me if I'm going too fast. Let's see, I know mass 1 is 21, mass 2 is 16, velocity 1 is 2.4, and that's it. Alright. So, 21 kilograms, 2.4 meters per second equals 21 kilograms V1 prime plus 16 kilograms V2 prime. Can't really go any further there, right? Because I have one equation, but how many unknowns? 2. So I'm kind of at an impasse. This is why it's good that it's an elastic collision. Because if it wasn't, I couldn't do anything. So now I'm going to drop into kinetic energy. And so KE1 plus KE2 will equal KE1 prime plus KE2 prime. So total kinetic energy before equals the total kinetic energy after. Substituting in for kinetic energy, M1 V1 squared plus 0 here again because I know my V2 is 0, it wasn't moving. 1/2 M1 V1 prime squared. 1/2 M2 V2 prime squared. Can I simplify that at all? Is there anything in every term that maybe I could get rid of? The 1/2, right? Oh, sorry. We can put a 1/2 in front of the 0. You said mass? Yeah, but there's different masses. So I can simplify this and then substitute in. So I'd have 21 kilograms times 2.4 meters per second squared equals 21 kilograms times V1 prime squared plus 16 kilograms V2 prime squared. And again, I'm stuck because I again have an equation with two unknowns and I can't go any further. But if I look at this equation and this equation, do they have anything in common? Same two unknowns, right? And from your algebra class, if you have two equations with the same two unknowns, life is good, it's solvable. So now it's just algebra. I'm going to do the algebra using, I think I'll use Wolfram to do it, quite frankly. I could, solve one of them for, say, V1, substitute it into, V1 prime, sorry, substitute it into the other one, then I'd have just one unknown there and solve that and go back. I could do all that. Which one would I solve for V1 prime? Probably the red, because it wouldn't involve a square root. That's probably what I would do. But if I was to do it by hand. But I'm going to use Wolfram to do it. So I should go, let's see, here to our links page. And remember, I think any of these would actually do it for you. I just happen to like Wolfram. So 21 times 2.4 equals 21 times, I think I'm going to call my V1A plus 16 times B. Now, to put it in two equations, I do comma, space, and then I can put in my second equation, which for me is 21 times 2.4 squared, which equals 21 times A squared plus 16 times B squared. So it gives me two scenarios because it's just mathematically solving it. The one where both of them are moving after, and the one where A is still moving and B isn't moving. Well, that is actually, if A missed B, that second scenario would happen. But that doesn't happen, so it must be the two above. So now I have my answers for V1 prime and V2 prime. 0.324 and 2.72 looks like. And I hope those are correct. Probably makes his head a little bit bigger. So check yours, I'll check mine. We'll see how we come out in the end here. So be careful when you're entering your answers. They want stone 2 first, and then stone 1. 3, 2, 4. Oops, they only want 2 sig figs, so I don't want it to yell at me. Alright, on to number 7. We have Brittany standing on a skateboard, and I'm going to assume the skateboard is up. They're saying, hey, she's frictionless, basically. And she catches this pumpkin, and she begins to roll backwards. So, well, this is a perfectly inelastic collision, right? Because we've got 2 bodies before, they combine to be a single body afterwards. Alright, so that's where I'm going to start my Y. This is a totally inelastic collision. Momentum must be conserved. As the 2 objects become a single object. You're welcome anytime. I'm going to also say they will move off slower than the pumpkin was moving before the collision. Alright? So now we gotta go diagram it, right? Momentum of the pumpkin. Momentum of Brittany and the pumpkin. Momentum of Brittany equals 0. Yeah. I don't know why I pictured it going to the left, but I did. I'm just going to call the left positive, though. Questions on the diagram as part of my Y. Alright, let me get it into my stuff. Yay. So, from the equation sheet, I'm going to grab that momentum of the system before equals momentum of the system afterwards. Right? And let's see, beforehand, I had momentum of Brittany plus momentum of the pumpkin, And that's going to equal afterwards the momentum of this new body Brittany pumpkin. And I'm going to call that direction positive. And again, of course, I forgot all my vectors. Good? So I know this one is 0, because she's not moving. This would be the mass of the pumpkin and the velocity of the pumpkin. This one, the mass will be the mass of Brittany plus the mass of the pumpkin and the velocity of Brittany pumpkin. And then I can substitute and solve. Because I know all those. I have the mass of Brittany, which I'm considering the skateboard as part of Brittany. I have the mass of the pumpkin. I have the original, I have the speed of Brittany and the pumpkin. So in here, the only thing I don't know is the velocity of the pumpkin. And that's the only variable I'd have when I substitute it in. Questions or clarifications that I can do? Can you say it again? All right, so on to number 6. And 6, we have a hammer hitting a rock that's lying loose on the ground. And they're telling us that it is elastic. So now again, I have a smaller. I have a bigger hitting a smaller again. So again, I'm going to think the hammer is going to keep moving forward. Maybe not, but I can tell that from positive and negative afterwards. So I'm going to guess that. So collision is elastic. So both. Oops. Momentum and KE are conserved. The hammer will keep moving forward after hitting the rock, but move slower and slower than the rock. So I'm predicting the hammer's going to hit it, the rock will move off, and the hammer will keep going, but slower than the rock, and also slower than it had been going before it hit the rock. All right? So, need to do my diagram. Let's see. Ground, rock. Hammer. Hammer. Rock. So, momentum of the hammer. Rock isn't moving. Momentum of the hammer afterwards. Momentum of the rock afterwards. Momentum of the rock before is 0. Yeah, that's better. Momentum of the system equals to the system. Okay, E system. Oh, this is all like number 10. Right? Right, that's all exactly from 10. So, momentum of H equals momentum prime of H. Since we've just done one like this, I'm kind of truncating my steps a little bit. Mass, initial velocity of H, mass of H, velocity prime of H, mass of the rock, velocity of the rock prime. I can substitute in there. I won't find an answer, so I'll have to move on to my kinetic energy just like last time. So I'll do kinetic energy of H, energy prime of H.
You know, that was not quite correct.
And then do the same math I did before. So 6 and 10 are like kind of identical to each other.